Yeah, hopefully it will make it clear after the talk. So I'll present 3D magnetospheric accretion simulations and with closing exoplanets. So as we know, magnetospheric accretion basically is a combination of closed, rotationally supported disk accretion and magnetically supported spherical accretion. So it's a combination of both. And because of the accretion process, this accretion process happens at the deepest part of the potential. So it released most of energy during the accretion process. So it released a lot of UV radiation and also a lot of lines. So that's why we have a lot of these observations which probe these physical processes. And these excess emission from above the stellar photosphere, all of these emissions actually come from the hotspots at the surface of a star due to the inflow. And Hubble Space Telescope spends 400 orbits and observes 71 young stars in this Ulysses program. So we have a lot of observations on magnetospheric accretion. And with these data, you could actually, by fitting these excess emission, you could actually probe how the hotspots distributed at the surface of the star. So you have some hotspots with hotter temperature and some hotspots with a colder temperature. You could actually tell them apart. And by monitoring these UV flux over time, you could actually even figure out all the hotspots may rotate with the central star. So we could get a lot of information on the magnetospheric accretion from these observations. So although we have a lot of observations on magnetospheric accretion, on the theory side, it's actually not quite clear. The earliest work by Gaussian and Lamb suggests that this is very turbulent, so these magnetic field lines is only moderately bended. In that case, the disk could accrete steadily. You could have a steady accretion. But some later work suggests that maybe the disk is not that turbulent, and your magnetic field lines, which connect with the star and the disk, they will twist, either by the disk rotation or by the stellar rotation. So whenever the magnetic field lines twist, and they will reconnect and generate these bubbles called field inflation. In this picture, magnetospheric accretion is non-steady and it's episodic. Simulations have been carried out to study magnetospheric accretion, but because this is expensive simulations, most of the previous work we're doing with 2D or with some non-ideal MHD effect. But the 3D simulations, ideal MHD simulations have been carried out, but focus on the inner part of this magnetosphere. Okay. So recently with Athena++, we did these, we have this special grid structure so that this allows us to resolve both of the star and the disk very well. And we can run these simulations for 2,000 innermost orbits of the star. Okay. So you have seen this movie, the disks orbit around the star and is magnetically truncated by the stellar magnetic field. So this is the star has a dipole field. This is not a clean cavity. You can see some of the edge, at the edge of the magnetosphere boundary, you have filaments moving in. And sometimes these filaments could, play the movie again, and the filaments will climb the magnetic fields while they're moving in. Okay, so they will form this onion shell structure. They have many, many accretion columns. It's very dynamic. So this is our previous work. And in this talk, I'll particularly talk about how the stellar spin, if we allow the central star to rotate, how the stellar spin will affect this accretion structure, and how the stellar spin will affect the hotspots, and how it will affect the accretion and outflow structure. And finally, I'll talk about what's the torque between the star and the disk, whether the disk could torque down or torque up the star. Okay. So first, if we make a polaroidal cut in the simulation, we can see that this picture is very different from traditionally magnetospheric accretion picture. You have a thin disks, but here you have very thick disk. In the simulation, the disk initially was very thin. The scale, its H of R is 0.1 or 0.05, so it's a thin disk from thermal point of view. But from the density point of view here, it's actually very thick. That's because it's magnetically dominated. Okay. So you have this thick magnetized layer. And this layer will accrete very strongly towards the central star. You could see that at the mid-plane, the blue dots, blue line here, you have a density drop. But at the surface, the density is more continuous. So you have a surface accretion. And this leads to a very large alpha. The alpha parameter at the truncation radii is close to 1. And this alpha parameter decreases with R. If we make a mid-plane cut, then we can see these fingers moving in. This is due to the interchanging stability. Basically, you have this high-density material beyond the truncation radii on top of the low-density material within the magnetosphere. So then, when you have high density on top of a low-density material, it's really Taylor unstable. Right? So then you have these fingers moving in. And this has been seen before. Okay. So now this is the previous case where do not allow the central star to rotate. But now if we allow the central star to rotate, then this introduces another free parameter. And this is the co-rotation radius in the disk. So this is where in the disk, the Keplerian orbit equals the stellar rotation orbit. So if you have magnetic field connecting these two, the field lines will not twist, will not be twisted. Okay. So then we have run many simulations. From the left to the right is the star will start to spin up. Okay. So on the left side, the star rotates very slowly. So the co-rotation radii is very far. So this is similar to our previous case where the star is non-rotation. So in this case, you can clearly see this, these filaments due to interchanging stability. And also you could see these magnetic bubbles generated. These are large-scale instability in the disks. And they are orbiting around the star at sub-Keplerian speed, highly magnetized. So, but if you allow the star to spin up, if you increase the star's spin, then you can see that these bubbles are suppressed first. In this case, you will have these filaments moving in. In earlier works, this is called the chaotic unstable regime, and this is called the ordered unstable regime. And in both of these cases, you have fingers moving towards the central star. And if you continue to increase the stellar spin, and then these filaments are suppressed. And in these cases, in the propeller regime, then you have very clean cavity at the center. So the first thing here is that the rotation suppresses the filaments. So the disk feature depends on the stellar spin. And the second is that because these filaments will eventually impact the central star and produce hotspots, that means the stellar spin will also affect the hotspot distribution at the surface of the star. If you have slow rotators, then the fingers could collide with the star around the equator. And then you have hot spots close to, let's say hot spot at surface close to the equator. But for fast rotators, you don't have these filaments, so they climb the magnetic field and with the traditional magnetospheric accretion, then you have hot spots at a high latitude. So if we calculate the energy distribution of the hot spots, we see that for the fast rotators, you have more hot spots at higher temperature. So you have polar accretion and you have hotter hot spots for faster rotators. Okay, so after this, we also study how accretion and outflow are affected by the rotation of the star. Overall, the accretion is relatively steady, and it's kind of consistent with some like TW Hydra observations. But outflow is very chaotic, and this is because you have this field inflation operating in the disks. You can see that these bubbles, when moving around the star, they twist the field lines. You have magnetic reconnection happening here. Okay. So if we measure the outflow rate with the accretion rate, you can see that when the star rotates faster, you have a much stronger outflow. Okay. So during the equilibrium spin state, which I'll talk about later, the outflow rate is around 10%. Okay. So finally, talking about the stellar torque. Okay. So I used the Las Vegas sphere to demonstrate this idea. So imagine this is a central star, and the CT is an accretion disk around the central star. Okay. So for slow rotator, the star does not rotate, the disk rotates. Okay. So imagine you have magnetic field line connect the star and the disk. But because the disk rotates, okay, the anchor point at the disk will be dragged forwards, and the anchor point and star will not drag forward. So in this case, the field lines will in the opposite direction as the rotation. The azimuthal direction will be in opposite direction at the star rotation. So this will give a negative torque to the disk. Okay. So in this case, the star will spin up. Or in other ways, you could think about that is that the field lines move in front of the star, so will drag the star forwards, spin up. And this flatness of this curve shows the fidelity of the simulation, that it reaches a very steady state. Right? So the star will spin up. In the opposite case, if you have fast rotator, the star will rotate fast and drag the field line forwards, and they will give you a negative torque. The field lines are totally opposite in these cases, and the star will spin down. So this is a self-regulated process. If the star rotates too slow, you will spin up. If the star rotates too fast, you will spin down. So you will be wondering, okay, where is that equilibrium point? So by working out a lot of simulations, you could measure the torque and find out this equilibrium point. And that should be the point where most of the young stars should be at. And this equilibrium point is around when the truncation radius is 80% of the co-rotation radius. So the truncation radius now is very close to the co-rotation radius, just slightly inside the co-rotation radius. And if you use a kilogauss star, this will be correspond to the star rotates at 10 days. So in this case, consistent with most of young stars' rotation. So this disk locking mechanism could actually explain a lot of YSO's rotation. So we do not have to revoke like a stellar wind. Okay. So this is the rendering of this equilibrium spin state. So first, the disk is thick, and you still have filament during this state, and you have hotspots close to the equator. You have very fast jet and wind, outflow rate 10%. So that's all. So to summarize, this is a traditional picture. The 3D simulation suggests a quite different picture. The disk is very thick and highly magnetized, very turbulent. And the spin actually affects the dynamics in the disks. Slow spin have these filaments moving in, have hotspot close to the equator. Faster rotator will suppress these filaments. And they have also much stronger outflows. And the equilibrium spin state, we could give a value here. And the hotspots, outflow, variability are all consistent with observations. And yeah, that's the end. And if you wonder, if we put a planet in the simulation, whether this planet will be really trapped at the magnetospherical truncation radii as we hoped, or a lot of theory invoked, wait for Wednesday for Arturo's talk. Yeah, thank you.
I'm going to exert privilege here. Could you go back to a couple of slides where you had like the wind part? You can see a wind. Yeah. Here. So, am I seeing a wind coming out polar?
Oh, the wind? You mean coming out from the...
Yeah. Or is that coming in?
These are magnetic field lines.
Oh, those are field lines.
Yeah,
okay.
These are magnetic field lines. Yeah, the wind is going out. Yeah, these are the field lines. And this is the toroidal component. So the field reverse direction here. So these reconnections generate these outflows.
Yeah, the reason I ask is that in TW Hydra, there's this evidence for something like a polar wind, which people say is like could be a accretion-driven stellar wind. Mm. Do you get any, because you have a very thick disk, can you actually get some ejection that's not at a very high angle to the polar axis?
Yeah, the outflow, there are, yeah, so there are, yeah, so this is the flow structure. So you have high velocity close to the pole, so this is very likely to be low density jets, around 500 kilometers per second.
So if you looked at a pole on like TW Hydra, maybe you could see it. Yeah, you could see a jet.
Yeah.
Okay, questions? Yeah, Eric.
So Eric Gaidos, University of Hawaii. So your torque, zero torque state of 10 days, how sensitive is that to the field strength and the accretion rate?
Right.
Can you speak to that a little bit?
Yeah, so these simulations are actually scale-free because we don't have thermodynamics. So we don't have the stellar wind, which is driven by like a stellar high temperature. So we don't have stellar wind, and the temperature here are prefixed. The only free parameter in the simulation is the scale height, h/r of the disks. So if your field gets weaker, you could think about that the magnetospheric truncation are closer to the star. So you could still scale your simulation because the torque is almost flat. The simulation here, we have the thin disk calculation, which is this blue one is h/r 0.05. It's very thin disk, and they have almost the same zero torque equilibrium spin state. So in some sense, this tells us this spin state seems to be not very sensitive on the disk thermal thickness free parameter here.
So you're scaling it from RT to R co-rotation.
Yeah. So this is a scale. Yeah, this is also dimensionless.
So I can see you can.
Yeah.
So just an observational comment. I mean, most T-Tauri stars spin much faster than 10 days. 10 days is actually pretty uncommon.
Well,
we can discuss that.
Yeah.
7 or 8 days for the things with yeah. Doug.
Do you have to do some subgrid modeling to simulate your reconnection? How sensitive it is to numerical diffusivity?
Yeah. So we don't have subgrid kind of relies on the numerical dissipation here. So this one we can only do through the numerical resolution study. So we have done for the thin disk and thick disk. The thin disk has much worse dissipation. But these two results are very similar, give us some confidence. But again, if we want to do very careful or work, we really need to have subgrid modeling on the turbulence. But as most of MHD simulation have been done, we just rely on numerical dissipation. And the argument is that as long as the numerical dissipation happens at smaller scale as you are driving, as a driving scale, hopefully it's converged. But that really needs to be tested with the numerical resolution studies.
Okay. Tom Ray, Dublin Institute for Advanced Studies. Can I ask you about, I mean, it's a really, really nice talk, and, the suppression of the filaments when you spin up the star is quite a nice result. But we also learned earlier on that the field isn't a simple dipole in many cases. So what happens in terms of those filaments when you start putting in octopolar fields or whatever?
Right.
The picture would get much messier, I presume.
Right. When we include octopoles, you expect they will affect more about the hotspot on the star. Because field around hotspot of the star will be very different. However, regarding the truncation radii, then the dipole will dominate because dipole decreases much slower than the octopole. So the truncation radii will be mainly determined by the dipole field in the system. The higher order mode will decrease like 1/r10 to the 16th power. So it will be very, very fast decrease. So the truncation radii will be less sensitive to the higher order, but the hotspot at surface will be affected. Yeah.
So in these simulations, Ralph Pudritz, you say that the stellar wind, you don't need that.
Yeah.
You do have a stellar wind in your simulation, and I'd wondered if you'd calculated the torque that wind exists on the star and compared it to this mechanism that you proposed.
Yeah, right. So in the wind, actually, in the simulation, we have very little wind directly from the star. That because here the density you kind of see to make it, they have a little actually info because we have some numerical density floor. No, we don't have corona, so we don't have corona. However, you do have these field lines connect from the star to the disk, so they were kind of pumping energy by twisting. So depends on how we define the wind. So if you consider those field lines as twisted up, like twist up burst, those can be considered part of the stellar wind. But we don't have corona. We don't have the traditional stellar wind, high temperature stellar wind or Parker wind.
The accretion power wind wouldn't be a standard stellar wind, though.
Yeah.
It's a very different animal.
The accretion powered wind. Yeah, we don't. First, our simulation won't be able to get this one because this whole region close to here they are infill due to the density floor added. So there is no directly outflow from the close by region. All the wind here is connected, is generated in these regions around the surface accretion region.
Okay, let's thank Zhaohuan again.